G'day there, you're watching the Aussie BIM Guru, and today I'm going to show you how to do wall penetrations using Dynamo. So I'll sort of run through what they are first, I guess, for people that aren't aware of the terminology. So a wall penetration, or in Australia what we call for slang penos, are basically a hole in a wall or a floor or a ceiling in order to allow something to pass through it. So most typically the most common types of penetrations are shaft penetrations through the floor, which we use shaft openings for in Revit, but structural wall openings are a little bit more tricky. Because we get so many different shapes and quantities of elements passing through walls, and there's a lot of ways to do it, but Dynamo is a good way to save time by reading the element geometry and generating a penetration automatically. So that's today's goal. So some requirements for the script are that we're going to get it to do either rectangular or circular openings, and we're also going to get it to allow for tolerance around elements as well, because we don't always want to have the penetration hard up against an element. Sometimes you want to have just a little bit of wiggle room, because some things will move or have separation requirements, or maybe there's something going around it, like a bit of fire insulating material. So the first question, I guess, that I asked myself when I did this was which type of family or workflow do we want to use? Do we want to generate wall openings, or do we want to place something like, say, a window? And there's some merits to the latter. So wall openings are instance-based. You place them on a one-off basis, and they're not driven by any type properties. They can't be tagged, they can't have shared parameters added to them, or they also can't be infilled as well, because penetrations are often infilled with something like a fire-rated material around the elements in them. So sometimes from a BIM perspective, we may want to fill that opening as well. And they can't be scheduled either, as far as I know. Windows, however, are type-based, can be tagged, can have shared parameters, can be infilled. They don't have to be empty necessarily. They can have an opening, but you can model things within that opening, and they can be scheduled. So it seems to me like Windows were the clear choice for what I wanted to get my script to place for me. So the clear choice. Maybe not the most standard workflow. I know a lot of structural engineers will use wall openings. I assume that's because there must be some properties they have with how they behave with reinforcement. But I have seen them use windows as well, so I'm not sure if there's any true winning property to using openings. Anyway, some challenges. The geometry that passes through these walls doesn't necessarily hit it at 90 degrees. It's not necessarily going to be coming through as a square. It might be a pipe, it might be a few pipes, it might be twisting, it might be raking. So it's going to have to be able to deal with all these scenarios when it generates an opening. So the custom nodes we'll be using today to generate the solution are Zebra for the if node and Springs in order to place windows by points. And we're going to be using Dynamo 2.0.3, but I believe that this method probably works in most versions of Dynamo. Anyway, without further ado, let's jump in our Revit model. So I've just set up a wall. Note that the wall isn't at 90 degrees. It's important that we build this so that it can handle walls at any angles. You'll see why this is important when I build the script. Likewise, I've just set up a few elements. So I've got a duct running at an angle but linear. I've got a beam that's going through at a rake and a twist, and I've also got a set of pipes going through at an angle, as well as a pipe just hitting the wall at 90 degrees. So we're going to try and build a script that can handle all these scenarios when generating penetrations. So let's jump into Dynamo, and I'll just set something up on the side so I've got my reference. I realize I don't have my reference available. So we're going to build a script that can basically generate a window in the position of our penetration. So the first thing that we need to do is actually get the elements that we're triggering the penetration from. So we're going to get a select model elements node, and this will be the node that we use to pick our elements that are going to cause the penetration. So let's start with this set of pipes for, I guess, our script building scenario. Okay, so we've got 3 elements, and we'll get our wall as well. And the reason I'm just getting these first is so that I can maximize Dynamo now, because we have these inputs available. So this is going to be our penetrating elements, and this is going to be our wall. And I'll just make these inputs as well, because we're going to run the script in Dynamo Player at the end. Okay, so the first thing we're going to do is get the element geometry of our elements that are going to be causing the penetration. So we'll just run our script and do a zoom fit, and there we go. That's the geometry of our pipes. And likewise, we're also going to get the geometry of our wall. There we go. So what we'll do is just turn off the preview for the wall for now. So what we need to do with our geometry is we'll flatten it. And we need to note that sometimes people might select things that don't actually have just solids. So we need to process out anything that isn't a solid from this list. At the moment, it should just be 3 solids, but we need to make sure that we can handle, say, if someone adds a line or something like that, because sometimes it might be a family with model lines in it. Okay, so I'm just going to check the object type to check all the types, and I'll just run this. And at this point, we should be able to see that we have Autodesk Design Script Geometry Solid. So we need to find all elements that type contains the word solid. I believe that should separate all the other elements out that we wouldn't usually use. So I'll do string contains, and we'll check that this contains solid, and we'll just, we will ignore case. So essentially this method would allow us to apply a filter by Boolean mask on my favorite nodes, and that would essentially remove anything that doesn't provide a solid to Dynamo, because we only really care about our solid geometry. What we're going to do is just join those solids with a union at the end to turn them into just one solid instead of multiple. Because back in this sublist over here, we have 3 solids, and we just want to deal with one for our intersection. So I'm just going to turn off my preview for all these and just leave on my solid by union, because now this represents just one solid. Okay, so now we can take the geometry for our wall, and we can do a geometry get intersection. And we'll get the intersection between these 2 pieces of geometry. So I'll run my script, and now if I just hide my solid by union, you'll see that what we're left with is actually the elements as they penetrate the wall. So if I just turn that preview on, you'll see that it's a bit hard to see because the wall's obviously on top of it, but that is the element as it passes through the wall. So this is essentially what we're going to use in order to test this. So what we need to do now is we need to deal with this element. The first thing we're going to do is we're going to get the centroid, or the center of that group of solids, because we should just get one solid. And I'll just run this, and this will give me a point in the middle of that geometry. And the reason I'm getting this is because we're going to have to generate a bounding box around these elements. But it's important to note in Dynamo that bounding boxes don't quite work the way you think they would. So if I do a bounding box by geometry, you'll notice in the description it said it's going to be axis aligned. So remember that our wall is on an angle. So we're going to just do bounding box to cuboid, and we're just going to turn our bounding box into a solid so you can see it. Cuboid to cuboid. Okay. So you might think that the bounding box is going to line up to the wall face, but unfortunately it doesn't. Note that our bounding box is actually rotated to Dynamo's true north, or Dynamo's north reference. Essentially the Y plane, or the XY plane. So that's not ideal. We actually need to rotate to this plane in order to get our true intersection to find out our penetration. So we're going to get rid of those 2 nodes for now. And what we need to do is find the wall's orientation as a vector. So we're going to get the location of our wall, because in Dynamo, wall locations are represented as the line that underlies its orientation. I'll just check. I'll see, get existing element location. Can be hard to find the location though sometimes because there's so many nodes that have get location in them. There we go. Get an existing elements location. I'll get my wall's location, and I believe that I want to get the wall's location, not the geometry's location. There we go, and that's our line. And we're going to get the start and the end point of that. So the start point and the end point. And I'll just take those. And that should give us 2 points at either end of our wall. And we can see them there. One here and one there. So using these points, we should be able to find out the orientation of our wall versus Dynamo's north. So what we'll do is we'll get a vector by 2 points. And we're going to build 2 vectors. So the first one we're going to do, alright, we're going to translate the origin point of our wall. So we're going to translate with direction and distance, and we're going to translate the start point of our wall. So we want to make a line that's pointing up to Dynamo's north. So we're going to translate this in the direction of the x-axis. And we're going to just translate it by 1,000 or a meter. So just something nominal. Okay. And that should give us a point at Dynamo's north So pointing this way from our start point. And what we need to do is get a vector by 2 points. So we're going to go from that point to the end of that point we've just created. But we're also going to go from the start point to the end point and get 2 vectors, because we need to compare these to find the angle that we need to rotate our intersection geometry around to find its true bounding box. So we're going to get a vector angle about axis. And from there, we're going to take this vector and the other vector, and our rotation axis is going to be the z-axis, because we're checking how far rotated it is around z, pointing up. And that should give us an angle telling us our angle. So we can see we're roughly at 45 degrees, which is correct. That is the rotation I've set my wall to. So I'm pretty confident that that's looking pretty good. But from there, we're just going to deal with, we need to process this a little bit. So I'm going to go backwards from here. So I'm just going to times it by -1, because we want to rotate back, because our wall is going to be perpendicular to the orientation of that vector angle. You'll see what I mean when I rotate my intersection geometry. So now we need to rotate our geometry, because we're going to rotate that intersection geometry. So we're going to go by axis and by degrees and origin. So our geometry is going to be our intersection geometry from back here. Our origin is going to be the center of that geometry. So we're just turning it around at center point, which is why we got the centroid. In this case, the axis again is going to be the z-axis. And the degrees will be this negative rotation here. So if I just zoom over here and I run, see, we'll get a set of elements that are now orientated at Dynamo's north. So now we can get a true bounding box around these elements at the same orientation as the geometry itself. So we've basically just turned this around. So what I'll do is just temporarily turn off those elements. So now we can see that we're working at an orientation that Dynamo can work with. So what if I grab a bounding box now? Now we are working at the same orientation, so we can truly get a bounding box that makes sense. Remember that the pipes are also at an angle to the wall, as well as the wall being at an angle, so that's why it looks a bit funny. Okay, so we're just gonna do that. We're gonna get the bounding box and we're gonna turn it to a cuboid. Cool. And I might just stop previewing my geometry and we'll just deal with our bounding box for now. So from here, we need to find out the properties of our bounding box. So we need to find the cuboid width and the cuboid height, because these essentially will let us know the penetration size we need in order for this element to clear our wall. Great, so we'll just get those 2 sizes. But now we need to add some tolerance potentially. So what I'm going to do is just get a number slider. And I'm just going to start at 0, because sometimes we do want to have a flush penetration maybe. And let's say we can go up to 500 mil of tolerance either side, and we'll just go up in steps of 50. That way we can just apply some tolerance to our opening if we like. And I'm just going to call this tolerance and make this an input as well for Dynamo Player. I'm going to build a code block now, and I'm just going to say the bounding box width is a variable, and we're just going to do plus increase tolerance. Then I'm going to do bounding box height plus increase tolerance. So I'm creating 3 variables here. So I'm creating my bounding box width, my bounding box height, and my increase tolerance. Whoop, mouse went a bit funny there. Okay, so now we should have the size of our bounding box with the increased tolerance as well in that code block. So I'm just going to turn off my bounding box to cuboid as well, so we're no longer seeing our geometry, and I'm just going to go back and turn off these points and lines as well. So I'm just going to turn off the preview for that, and also that. And I'll just turn off my centroid as well, and my translated point. So now we're just dealing with code at this point. Okay, so pretty much all we need to do from there is place our opening with those dimensions. So what I'm going to do is just get a spring hosted instance by points. And this is essentially going to be our window. So I'm going to take logic if, and I'm going to get a logic if node from Zebra. And the reason I'm doing this is because one of them I'll load is a rectangular opening and one is a circular opening. And essentially we're testing here, do we want a circular opening? And I'll show you how I've built that opening after as well, because that's quite important. But from there, we just want to get a window family. So we'll get family types. And it's up to you whether you make these a Dynamo player input. In my case, I won't. I'm just going to get the actual opening family I've built. So I'm going to get my circular opening and my rectangular opening. And if it is circular, I'll make it that it's the circular family. Otherwise, I'll make it that it's the rectangular family. So they're actually two separate families I've constructed. And that will be the type that we feed into our Springs hosted instance. The point is going to be our centroid of the intersection. So this centroid point is really important. It actually does quite a lot of things in the script. In this case, our type will be this. Our host is going to be our wall all the way back from the start. So we can go back and get that. And the last thing we need to do is set the size of this family after we place it. So we're going to get a set parameter value by name. So set parameter by name. And we're going to set two parameters. So we're going to set our width and our height. So of that family, we're then going to set width and height. And you may have different parameters in this case. It's up to you how you've named them or built your family that you're placing. And our values will be our two values from here. And that's pretty much it. This should create an opening now for these elements. So I'll just go back into this view and I'll just orientate so we can see this. And I'll run my script. And there you go. You can see that it's created a window and it's set the size just so everything can just clear this. Obviously I can undo this and I can go and add some tolerance to this element as well. So I can add, say, 200 millimeters either side. And you'll see that now we get clearance around each side of the element. So you can really start to see the strength of this workflow and just how easy it is to use. And obviously we can pick a lot of types of elements. So I can go and change this to my beam over here. And I can select this instead and run. And I can make an opening tolerance around here as well. It's just all based on that intersection geometry and the bounding box that knows how to encapsulate it. And the rotation to go to Dynamo North is really critical. But what I might do now is just show you the opening family really quickly. So essentially it's just a window that has an opening that is centered around the sill. So this is the sill height in the window. So I haven't changed that. I deleted the top plane and I've just created some extra reference planes for top and bottom. And I've done an equal relationship on the center. So essentially this is the host point of my window, or its sill height as it perceives it. Likewise, I've just got a width and I've just made them instance parameters. So you can see I've got an instance height and width. And that's pretty much it. That's all I've had to do to the generic window family that comes out of Revit. I've also got a circular opening family as well. So if I just swap this over to circular opening, I'll show you how this one works as well, because this one's quite important. So essentially a circular penetration needs to be big enough that the longest side of penetration will clear. So basically what I've done is I've kept the family exactly the same, but I've added the parameter called radius. So this circle basically has a radius parameter within it. And the radius has a formula that says if the height is greater than the width, make the radius height on 2, because I want whichever side is bigger to drive the radius. And then otherwise it's width on 2. So it's always the larger side of the 2 that's driving it. That way the formula can still work the exact same way. It just pushes the values into a circular family or a rectangular family instead. Let's run this out of Dynamo Player now. So I'm just going to save this family. And I'll open up Dynamo Player, because this is where it becomes more interesting, because now you can see just how quick it is to set up penetrations for multiple elements at the same time. And I think just really try to understand the reason why I've had to rotate the bounding box geometry. So play with bounding boxes in Dynamo in order to understand why that has to happen, because it's quite confusing, I think, for those that haven't seen bounding boxes in Dynamo before. Okay, so I'll just open up my demo script that I've just built. And we should have our inputs that we set in Dynamo Player before. So now we should be able to apply penetrations to all these elements. Fingers crossed. Sometimes Dynamo Player takes a little while to get started. Okay, cool. So you can see these inputs that we've set. So let's just start with our pipes first. And we'll just say that these are our penetrating elements. And we'll say that this is our wall. So we'll pick our wall. And let's just say 0 tolerance in this case, and not circular. Run, and there's our penetration. So easy. Let's do a circular penetration. So yes, we'll do a circular penetration. Let's say we want 150 mil tolerance, and we'll set this as our element, and we'll run. And there you go, it's created the circular penetration with 150 mil of tolerance in this case. Well, 75 mil either side technically. And let's do this really complicated element here as a rectangular penetration. Let's say we want 300 millimeters of tolerance. And we'll run, and done. That's how easy it is. So it's really simple, right? It seems like a complicated thing until you build the script, and then it all sort of makes sense from there, I think. We can do a mechanical penetration from mechanical engineers. So select this, run, and we've got a duct penetration. So there we go. And because I made them windows, I can actually tag them as well. So I built a tag here that just pulls out the width and the height. So I'll lock the orientation of my view, and I'll just tag them. And there you go. You can see that it actually tags the size of the opening. And I've also added it so you can add comments to them as well. So if you add a comment, the tag will pick it up. So let's say it's a mech penetration. And there you go. It's a mech penetration, and we can schedule these as well. So really powerful. You could obviously build the family to only accept increments of say 25 mil if you want your penetrations to be a regulated size, because obviously this isn't a very standard size for a penetration. But there's a lot of ways you can play with the family to add a lot of controls and tolerances to the way the family behaves as well. Which I think is another reason why the window category makes so much more sense than the wall opening category in this case, because there's so much more you can do with window families. So that's pretty much all for today. Hopefully that's helped. I know there's a couple of people on LinkedIn that I said I'd send this along to, so I'll definitely let them know about this video, I guess. And if you see it, feel free to let me know if it helped you. And hopefully it helped other people as well. So thanks for watching today. If you're not already following and subscribing, feel free to do so. I upload videos about 3 times a week, most of them focusing on Dynamo. So hopefully I'll see you in future videos. Thanks. Take care.